There has been an obvious pause in covering of geometry of sets, and that is due to some delicate questions about Frostman's lemma. So let's recall this lemma, which says that for a Borel measurable subset of the Euclidean space, its Hausdorff S measure is positive, possibly infinity. That is one of the detailed points that justifies my making yet another video on Frostman's lemma. So the important case of infinity. If and only if, so this theorem ties the positivity of S-dimensional Hausdorff measure to the existence of certain Radon measures with a upper bound. So if and only if there exists so let's see, right, a Radon measure, so this is Borel regular measure that is finite on compact sets. So here, in fact, we want it to be with compact support. So with compact support, such that the measure of Rn is finite and positive. So I'm following Mattila's book. And the important part, that the measure of any ball, not necessarily centered at the set, but Rn and any radius, the measure of the ball is bounded from above by S power of the radius. Okay, so again, the S-dimensional Hausdorff measure of a set is positive if and only if you can find such a measure. So it's a double-sided strong claim. We've seen applications of this theorem to estimating Hausdorff dimensions of A cross B, but later also we will use this to prove that capacitary density of sets coincides with capacitary dimension of Hausdorff sets coincides with Hausdorff dimension of them, which is a very strong tool in all kinds of projection theorems and more. Okay. There are several things here. As soon as you allow this infinity case, something obvious happens. So if t is strictly less than s, then ht of the set is also equal to positive infinity because of Hausdorff dimension, basically. So therefore, there also exists such Borel measures satisfying measure of balls comparable to t power of this. But how could this be possible for varying powers of t? The point is that we only need, so this will need a little of thinking on your part, need to satisfy inequalities of type star only for radii less than or equal to 1. So it's kind of, it happens on the local scale. So the difficult part of getting such an inequality is in the for small r, because, well, measure of the ball, the whole ball, is less than or equal to measure of all of our n, which is finite. So it's some constant number. In particular, by multiplying in a big enough c, we can make it less than r to power t for r bigger than or equal to 1 for the right constant c. So we can have it happen for large values of r. Of course, if we want to avoid any constant c here, you just change u, replace with u divided by c. So the issue is only for small values of r. But then for small values of r to power t is indeed bigger than r to power s if t is smaller than s, because it works the wrong way. Okay, so that explains why this isn't in any apparent contradiction to having the same for various values of the power. The next point is one of the first questions that comes up when you try to think of what this Frostman measure does is that isn't mu just the Hausdorff measure of the set restricted to E? So this is a Radan measure because E is Borel. I'm not sure if it's really necessary, but just it is definitely so if it is for any measure. And well, we require that measure of all of our n be finite. So even in the so assume for this that for simplicity that the Hausdorff measure of E is finite. So in which case the mu measure of all of our n will be finite. Okay. Let's add also the positivity part, so that the technical part of having positive and finite measure is okay. Now, what this would mean, if this was the case, we would have the mu measure of the ball, so that will be hs of E intersection with ball of x and r less than or equal r to power s for every x and for every r positive. From which, if you divide and take lim in for lim sup, this would say that the upper S density of E at x is less than or equal to 1 for every x and for every r positive. But this is, we know, not the case. But this is not the case. For example, we saw that this double star is true only almost everywhere. That was one of the theorems, that if you started with a finite Hausdorff measure set, then the density in that dimension was less than or equal to 1 almost everywhere. So technically, this is not satisfied. But then there is more. So if this was only the problem with this kind of density point where density here is, so I'm looking at a set subset of R2 at dimension 1. This is 2 at this value. But then this can be resolved by replacing this mu by half of that. So 1/2 of HS measure restricted to E. So that can be taken away. So the only hope to kill the possibility that some multiple of HS is the Rodin measure is to have an infinite density point. The case can be infinitely worse, which means we can have a compact set with finite measure and positive, which consists of some line segments whose length shrink down geometrically, but they are at different angles at the origin. Then the density at the origin of this set E will be plus infinity. So no matter what, so for every constant that you can imagine, HS restricted to E divided by this constant is not a Frostman measure, because W star fails at the point 0. Okay. In this very example that you see, this bad example having 0 here, however, you could avoid the point 0 because remember, you only want a measure that satisfies this upper bound and is positive and finite, but it doesn't have to happen. It doesn't have to have anything to do with the set at all locations. Therefore, instead of looking at all of this set, we could only consider some parts away from the origin. We can even just take one of these green lines, in fact. In that case, so if you take F, F to be a compact subset of such that now HS restricted to F is the Frostman. Well, there's not a unique one, so is a Frostman measure. By the way, this notation of restricting a measure to a set means that to measure the measure of any set is simply this mu measure of A intersection with U. So that is the restriction of the measure to yes, so the restriction of the measure to the intersection with A. So that's the definition. So this claim that I made here is for this particular example. So the F will be the green set there. But it turns out, and this is key, that one can always find the right compact set. So a compact subset of E under the assumptions of the theorem, such that Hs restricted to F is a Frostman measure. Okay. Let's give an idea of a sketch of how this can be achieved. But very importantly, I want to do first the case of Hs of the full set is finite. So I exclude the infinity. We know that by this density, upper density theorem, which I already alluded to above, this Hs of B xr intersected with E divided by r to power s, the lim sup as r goes to 0 is less than or equal to 1 at almost every x in E. Okay, and the example we just saw shows that this almost everywhere is necessary. Then by this standard exhaustion, let's say, argument, there exists first you can find Borel, and then from Borel you can find compact by regularity of Hausdorff measures. So there exists compact set F in E for which this lim sup less than 1. So we know that at every x, first of all, throw away this negligible set of points where density will never go above yes, so the set where this will never go above I'm sorry, so there is first the negligible set where this does not happen, throw them away. For the rest of the set, at every x, this limit will go below 2 for some value of r and then onward. So it will begin to happen. And then this exhaustion is that you look at the set of points where less than 2, so this Hs of ball xr intersection with E divided by Rs, we know that this will be less than 2 at some point. For every value of x, this will begin to happen at some r value. So r, the threshold r, will depend on x. But this exhaustion trick, which is used again and again in geometric measure theory, is by saying, okay, for some x it happens after r is less than 1. And then for others it happens after it's less than 1/2 and so on. But one of them must have measure, positive measure. So there is this a compact set E for which these values are less than 2 for every x in F and every are less than some delta. So I must also add here that there exists some delta positive, and then some set F for which this happens, and also the set is not trivial. So HS of F is positive. Then it's easy, just it's claim mu equal HS restricted to F, but if you want to be strictly precise, maybe 1/2, and just to be safe, 1/4 is a Frostman measure. So I emphasize that I'm doing this for the case where I start with finite measure. Where was this used? This was used in this claim that the upper density is less than 1 almost everywhere. That is, it is necessary that you start with this, because otherwise you can have parallel copies and density is never 1. Okay, but then from that point on, it was just a matter of definition and playing with countable intersection and union of sets and things like that. Okay, so what do we do in case of HS of E equal to infinity? Okay, and that's actually the most interesting now part of Frostman. As we saw, if measure is finite, you can always find the right compact subset where just the Hausdorff measure restricted to that becomes the Frostman measure. Okay, here is this fact, and that is really highly non-trivial, which is more non-trivial, let's say, than Frostman's lemma, because if one has this, then you can easily get Frostman's lemma. And that fact is that then, under these assumptions, there exists compact E prime under E with HS of E prime, now finite and positive. So it's saying that if you give me a Borel set with infinite measure, there is some compact subset of it with positive and finite measure. And I said this is highly non-trivial. If you haven't seen this before, you would probably wonder why such a claim is even non-trivial. Of course, it's completely believable, but maybe if you consider other strange things in geometric measure theory, then you begin to see there is no reason why, in fact, this has to be the case. Simply because you have a big measure should not really mean that that you can extract some finite measure set out of it. Remember that S here is strictly less than n, so basically you are in a general metric space. There is no real help from the fact that you are living in a Euclidean world. Okay, so we go back to case 1. Okay, so this ends this proof. Proof of what? Proof of the claim that you can always find the right subset so that Hausdorff measure restricted to it is the Frostman measure for our set. But then this claim that you can always find a finite set, this is again a big deal in geometric measure theory. So Mattila's book, Falconer's book covered that. It is also true in metric space settings. Mattila proves it for compact spaces, but it is also known in more general metric spaces. Holroyd has proven a very general version of that. The proof presented in Mattila is following Holroyd's work. Let me then at least make this last claim more precise for future reference of you and me. That is E subset of Rn closed. So I'm coding from Falconer's book. Probably this is true for Borel, but let's be safe and keep it that way. And Hs of E is plus infinity. Okay, suppose that we have this claims, these assumptions, then there are two claims about this. Given any positive value C, this is a bit stronger than just the existence of a finite set. There exists some subset of E compact with Hausdorff measure of F equal exactly to C. So there is no gap. You don't jump all of a sudden. And number two, there exists some compact subset of E. This is exactly saying that the Frostman lemma, the restriction to the right set is Frostman's lemma, but I repeat it for the sake of completeness. Okay, such that Hs of F is positive and Hs of every ball intersected with F is less than or equal to B to Rs for some constant B. This is for every x in Rn and for every R positive. Falconer says for every R less than or equal to 1, I don't see any reason, because it just becomes easier to have this inequality if R grows. But I mention it in case. Okay, so that's some tricky observations regarding Frostman's lemma and its connection to existence of sets of finite parameter. Mattila comments that knowing this Frostman's lemma, it's difficult to obtain this other one. So we saw that if you know the result that there's always finite measure sets, you can go back to Frostman. But then he says, I don't know any easy argument of going in the other direction. I don't know if that has changed since this book or not, but I think that is enough for us tonight. Okay, thanks again for following this, cleaning up some questions, at least in my own mind, about Frostman's lemma. We will continue with the study of geometry of sets. Please do comment your questions, your suggestions for improving, and yeah, anything else basically. Have a great one.